introduce the rest of the chapter, which is really problem solving for chapter 32. Okay, I have introduced all this information, and I will say we're gonna solve like couple of problems here. Remember, the propagation direction is always given by E cross B, the direction of E cross B, the cross product between E and B. Now consider each of the following electric and magnetic field orientation in each case. What is the direction of the propagation of the wave? E equals here, E times I, unit vector, and B, it is minus B J unit vector. Now we can say here EI times negative BJ. Now when you cross multiply I by J, you're gonna get K, and E times negative B is negative EB. Then I will say S. Remember we said S, it's in the direction of the propagation, and therefore is going to be I cross negative J, which is negative K. For B, we have E, it's along the positive Y, and B, it is along the positive X, and therefore is going to be J cross I, and that is negative K. For C, it is E equals negative EK, and B, it is negative BI. Then it's going to be negative K cross negative I, and that is going to be J. The last one, it is for E, it is I, and for B, it is negative K, and therefore we're gonna, when you cross multiply I times K, is gonna give you a negative J, and we have a negative, then is gonna be a plus J. This is because we are going IK, we are going clockwise, anti-clockwise, then is gonna be, this is the way it should be. Now, this one here is about the electric field of a sinusoidal electromagnetic wave obeys the equation. Remember, we said this is E equals E maximum cosine. Here, this is Kx plus this is omega times t. Then these parentheses, they have omega, and here these parentheses, they have K. What is the speed of the wave? Now, relevant concepts here. The first one is we're gonna write the general form of E. E equals E maximum cosine Kx plus omega t. We're gonna look at the variables here and how they are really connected. Omega is 2 pi the frequency. K, it is the wave number, and it is 2 pi divided by lambda. T equals 1 over F, and E maximum equals CB maximum. Now, E maximum is 375, and K, which is the wave number, it is 1.99 10 to the 7 radians per meter, and omega is 5.97. The first thing we can calculate the speed of the wave. This was introduced during the lecture. Omega divided by K is going to give you C, and that is 5.97 10 to the 15 radians per second divided by 1.99 10 to the 7, and that is going to give us 3 10 to the 8 meters per second, which is a typical speed for an electromagnetic wave in vacuum. We know E maximum is 375 volts per meter. Then B maximum is going to be E maximum divided by C, and that is 1.25 micro Tesla. For number C, what are the frequency, wavelength, and the period of the wave? and then we're gonna find if it is omega times 2 pi, and it is 9.50 10 to the 14 hertz. Lambda, it is 2 pi over k, it is 3.16 10 to the negative m, and that is 316 nanometer, and t equals 1 over the frequency, then 1.05 10 to the negative 15 seconds. Now, this wavelength is too short to be visible. If you look at lambda, it is 316. Remember, the lowest is 400 nanometers for the violet. Fields from a light bulb, we can reasonably model a 75-watt incandescent light bulb as a sphere 6 centimeter in diameter. Typically, only 5% of the energy goes to visible light. The rest goes largely to non-visible infrared radiation. Then it's not very efficient, okay, and it is I will say, converting a lot of energy to thermal energy. What is the visible light intensity in watts per square meter at the surface of the bulb? What are the amplitudes of the electric and magnetic fields at this surface for a sinusoidal wave with this intensity? Relevant ideas here. The intensity, it is defined as power per unit area. We know that the intensity can be, this is one of the equations another equation that we can use. It is 1/2 epsilon 0 C times E maximum squared. And we know that the amplitudes of E and B are really related by this equation. E maximum equals C times B maximum. This is the surface area of the sphere. Remember, here we said that can be, we can consider it as if it's a sphere, and epsilon 0 is this value. We can calculate the intensity at the surface as P divided by A. This is the power, because it is 5% efficient, then it is 0.05 times 75 watts divided by the surface area, which is 4 pi times the radius squared, and that is 330 watts per square meter. If we wish to calculate the amplitudes of the electric field, which is the E maximum, then I can use this equation here. E maximum squared equals 2I divided by epsilon 0 C, and then take the square root to find E maximum. And from that, you will be able to calculate B maximum as E maximum divided by C. All right, that's it here for this question. For the next one, a sinusoidal electromagnetic wave from a radio station passes perpendicularly through an open window that has an area that is 0.500 square meters. At the window, the electric field of the wave has RMS value of 0.0400 volts per meter. How much energy does this wave carry through the window during the 30-second commercial? Then here I will say I, again, it is 1/2 epsilon 0 C E maximum squared. And from that, we will be able to say that this is if I want to find what is really the total energy passing through a window, the energy is going to be power times time. Then it is epsilon 0 C times ERMS squared times the area times T. Because E, it is power divided by time, and also intensity, it is power divided by area. Then power, it is, I will say, intensity times the area. Then I will be able to calculate the energy as these really numbers multiplied together. This one, it's another like application. An intense light source radiates uniformly in all directions at a distance of 5 meters from the source. The radiation pressure on a perfectly absorbing surface is 910 to the negative 6 Pascal. What is the total average power output of the source? Okay, we know that P average, okay, which is the total average power output of the source, it is the intensity times the surface area. The pressure, the radiation pressure, it is I divided by C. And then from that, I can say that the, the radiation pressure is I over C I said, then the current can be calculated as C times the radiation pressure, and then I can substitute that I in that is in this equation, and then this is going to be the intensity times the surface area, and this is going to give me the average power. This one here, consider a sinusoidal electromagnetic wave with fields E equals E maximum, J times cosine kx minus omega t, and B, it is changing also sinusoidally, B maximum K cosine kx minus omega t plus phi, and we have phi between negative pi and pi. So that if E and B are, if show that if E and B are to satisfy equations, partial E, these are really from your textbook, xt, the partial derivative of the electric field component y divided by with respect to the x equals the partial derivative of the magnetic field component z divided by time, and that one also is the other equation. If these true, or if E and B are satisfying these two equations, then we can conclude that E maximum equals C maximum and phi is 0. First, we're going to evaluate the partial derivatives of the expressions for EAY xt and BZ xt, because we need to find what is really that, that derivative. Then we did here have EY xt. Okay, then we're going to get it. This is really the, the component here. And then we're going to differentiate, and this is the result, and we are going to differentiate for the BZ also. We will differentiate also for the sign here, and for that sign as well, we're gonna show the expressions for these, and then we are going to assume that E equals this quantity from the given quantities, and this is B, and therefore we are going to say, if this is true, then what I have derived here is going to be equal K E maximum sine kx minus omega t equal plus omega B maximum sine, and from that I can say that phi should be 0, because if I want them to be equal, then comparing the two equation, phi should be equal 0, because look here, sine and sine. And then I can also K maximum equals omega B maximum, and from that I will be able to get the relationship that E maximum should equal CB maximum. Okay, this one also, derivation for the second part. Okay, and then again, comparing the two equations, you will be able to get the second equation that we have derived in our solution, which is B maximum, you know, should equal epsilon 0, mu 0, omega divided by K times E maximum. This one is also about calculation of the intensity, different equations, and I will say we have, as I said before, we have intensity can be calculated as P over A, the power divided by the area. It can be calculated using this equation. It can be calculated by this equation. All right, and therefore, for the first one, we have the power given and the diameter. Then we will be able to say the average energy density, that we will be able to say I equals P over A, 2.6 watts divided by pi r squared, and this is going to be the solution. For the second one, what is given, it is the amplitude of the electric field for 80 volts per meter, and therefore I'm going to use this equation, which is the 1/2 epsilon 0 C E maximum squared. For the third one, I will combine the two equations, this one and this one, and therefore we will be able to get this equation, and I will be able, to calculate this, because what is really given here, it is the amplitude of the magnetic field. The last, not the last, the one before the last, the surface is totally reflecting, then I can use I equals C times the radiation pressure divided by 2. And remember, the pressure, it is force divided by A, because here what you have, it is given the diameter of the cylindrical beam, and the total reflective surface is given for you, and therefore you will be able to use this is you will be able to use that. For the last one here, you will be able to combine this equation and this equation for U, and then you will be able to find that it is just C times U, and then you will be able to calculate that. Thank you, and have a